Hi, this is Gareth Davis, and I'm one of the researchers that contributes to the forecastingdata.org project. And recently I've been working on benchmarking TSMixer and all MLP architecture for time series forecasting. And I thought I'd just make a video today just to share with you some of my thoughts on the paper and how it works and some of the results that I've seen from my benchmarking experiments. So let's sort of dive into it. TSMixer came out about 18 months or so ago by various researchers at Google, and I actually, funnily enough, kind of remember exactly where I was when I first heard about it. I was waiting for my daughter to finish her gymnastics class, and I was waiting in the car scrolling through my sort of Medium recommendation posts, and I happened to see an article on there about TSMixer, and I kind of thought it was interesting at the time because it come out of Google, and I thought, oh, I must come back and revisit it. And here we are, sort of 18 months later, and this is the first chance, and I've actually really sat down and worked with it in any sort of proper form. So let's sort of have a look at what we're talking about here. The abstract kind of introduces the fact that TSMixer is a novel architecture based on stacking multi-layer perceptrons, essentially to help tackle the problem of multivariate long time series type problems. And at this time, prior to this work and another piece of work which was called R Transformers Effective Time Series Forecasters, there was a tendency to use a very sort of heavyweight transformer architectures which had some sort of variation of the name former, whether that's autoformer, fed former, informer, anything you like former. And the thinking is that these transformer architectures would be very effective at being able to pick out the time dimension cross relationship covariances, as well as the cross channel covariances. And in a multivariate type system, you are attempting to forecast multiple channels at once. So for example, if you want to have a scenario of forecasting the weather, you might have several things that you need to be concerned about. You might want to look at the temperature, you might want to look at the pressure, the air pressure. I'm sure that there are various other features, and the idea would be that for your forecast, your weather forecast, you need to forecast each of those individual features or channels separately but at the same time. And the air pressure would influence the temperature and vice versa. I don't quite know what the direction of dependency goes in that kind of scenario, but you kind of get my feeling that. So the idea is that by using collectively all of that information together in collection, in combination, you would end up with a forecast that would be more accurate. But generally speaking, it doesn't always kind of work out like that, and quite often just using a simple univariate model where you're just working on one channel, one thing at a time, so temperature at the time, or quite often turns out to be more accurate than trying to predict or forecast all channels at the same time. So that was kind of that, and so once this paper was released on these linear models, which show that effectively you can get a similar or better performance by using just a simple linear model, no non-linearities in it, then that kind of opened up the possibility of further research which looked at simpler models which weren't transformer based to solve these very long forecast horizon multivariate type scenarios. So that was why they were working on this. So if we kind of just dive into the paper, the first thing we're kind of presented with is this rather attractive, I think, model diagram, which kind of takes you through the overall process of what the mixer means. And what it's, if we kind of look up here in this, the very top of it, what it's trying to demonstrate is that when you have your input into a model, you typically have a tensor of 3 dimensions. And so conventionally you'd have the first dimension would be your mini batch. So each training example is kind of batched up. And then you have a second dimension, which would conventionally be your time dimension, which would be your historical context window, sometimes called look back window. And that's going to give you, per channel, the information you're going to need to forecast forwards your future time steps. And then you have a third dimension represented by C, which is your channel dimension. And so this would be each of your features for the particular use case that you're working on. And the principle behind their mixing model is that they sort of alternate these T and C dimensions, permute them so that you either have a block that acts on a tensor which is in that BTC structure, or and then you flip it around so that you actually swap the time and the channel dimensions around, so that you have a BCT tensor, and then that goes through a block. And then the idea being that by constantly sort of permuting those 2 dimensions, that you allow the model to gain information about both the time dependencies as well as the cross-channel dependencies. And so that's that's basically what we're trying to describe here. And then we have these very more sort of granular diagrams in the bottom, which just basically show NLP. And this is kind of like pretty much classic type of stuff, right? So we have a fully connected layer, and then a ReLU, and then a dropout, and then wrapped around this, as we'll see, there is a normalization as well. So let's move on. Let's just make sure we've covered everything on here. So figure 1, the columns of the inputs means different feature variants, and the rows are time steps. Okay, and then this design allows TSMixer to automatically adapt the use of both temporal and cross-variant information with a limited number of parameters and superior generalization, right? So, okay, so that is the other point. So we're not using an attention-based system, so we don't have a huge number of parameters. There's no sort of multi-head attention or anything like that. So the number of parameters really is kind of limited to whatever you're putting in your into your linear layers. So let's go forward. So they then start to talk about traditional models, traditional univariate models, and how they've performed well. And then again, they kind of come back to this point on transformer architecture. So the natural intuition is that multivariate models, such as those based on transformer architectures, should be more effective than univariate models due to their ability to leverage cross-variant information. However, Zheng et al., that's the D-linear and N-linear paper, revealed that this is not always the case. Transformer-based models can indeed be significantly worse than simple univariate temporal linear models on commonly used forecasting benchmarks. And from personal experience, I'd say that's definitely true. Doesn't necessarily have to just be simple linear models, it could be, I think a lot of univariate models tend to outperform at least on the short Monash time series forecasts, tend to outperform the sort of purpose-built long transformer type models. And that's something I can relate to. So we'll then move on, and they introduce this table here, which they can't describe, and we'll just go on to the description of it first. So this is all part of this related work, and what this table does. So table 1, we coarsely split notable works into 3 categories. Category 1 is univariate forecasting. Category 2, multivariate forecasting. Category 3, multivariate forecasting with auxiliary information. So here we go. So category 1, ARIMA, NBEATS, LTSF, linear, patch TSC is univariate forecasting. Yeah, I wouldn't say I necessarily agree that LTSF linear or patch TST are univariate models. They were both multivariate models. You can run them as a univariate model, but no, they were, I'm pretty sure that they were designed for multivariate support, so I wouldn't necessarily agree with that. NBEATS for sure is, and in HITS would be as well. But okay, I'm sure it doesn't matter. Then they have category 2, so multivariate models. So anyway, they kind of say, oh, univariate just extrapolate temporal patterns. Multivariate extrapolates the cross-variate information as well, and in that sort of category they have all of the former models: informer, autoformer, pyroformer, fedformer, blah blah blah. If it's got the former in it, then it goes in that camp. Fair enough. And TSMixer, so their work kind of goes in here, and then they describe, let's just make sure we've got all the information from that. Okay, so sorry, let's category 2. So multivariate time series forecasting with deep neural networks has been getting increasingly popular, with the motivation that modeling complex relationships between covariates should improve the forecasting performance. Yeah. Former-based models, transformer-based models, category 2 are the common choice for this scenario, which was true at the time because of their superior performance in modeling long and complex sequential data. Vaswani et al. Is the attention is all you need paper. And then, Zeng et al. So category 1 showed that you can use a linear model, although, you can use a linear model to get the superior performance, although I disagree that it's a univariate model. Then there are other works that consider a scenario when auxiliary information, category 3, such as static information like location. So location doesn't change over time. So if you have an electricity meter, then it's stuck in its location. And future time varying features, e.g. promotion. So, common sort of classic sales scenario. We have a promotion on these days. How is that going to affect my sales performance? Which is obviously time dependent because they happen on specific days. So these include commonly used forecasting models have been extended to handle these features. These include state space models, which I think was an Amazon model, and RNN variance, Wayne et al. And Salinas et al. So that's DeepAR. And limit out, I think that might be LSTnet. Or no, maybe that's temporal fusion. That's TFT, temporal transfusion. No, try that again. Temporal fusion transformer. Thank you. Right. Anyway, those real-world time series datasets are more aligned with this setting. and why these deep learning models have achieved great success in various applications that are widely used in the industry. Yeah, fair enough. However, I would disagree. So I would disagree that these are multivariate models. They are univariate models that use cross-variate information to predict a single value or forecast a single value. You're not trying to forecast multiple things simultaneously. So yeah, I think the key thing here for me is that they're using auxiliary information, but I would say that they are using this cross-variate information as their exogenous variables, not as a means of forecasting multiple channels simultaneously. Okay, right, let's move on. So, linear models for time series forecasting. So they are okay. So basically, here they're talking about the linear model, D-linear, in-linear. So this work by Zheng et al. And trying to come up with some reason as to why they would perform better than a more powerful transformer or RNN type model. And so they talk about here, so let's say we consider the task of predicting some forecast of values from a set of time steps and across a set of channels. And in this work, we focus on the case where past values of the target time series are included in historical information, historical observations. So their premise here. So their premise here is that they are trying to forecast a set of channels which can be less than or equal to the total number of channels that you have as your input. Okay, that kind of makes sense. A linear model learns parameters. So it learns the weights and learns the bias across to predict the values of the next time step t as this linear equation. For most time series forecasting, most impactful real-world applications have either smoothness or periodicity in them, as otherwise the predictability is low and the predictive models would not be reliable. Okay. First, we consider the common assumption that the time series is periodic. Holt 2004. I mean, I'm guessing they're talking about Holt Winters there, which kind of makes sense because Holt Winters is classic sort of ETS model, and what they're talking about here is smoothness and periodicity. So they're talking about the trend and the seasonality component of a time series. I wouldn't necessarily agree that that is strictly true. I mean, obviously, okay, let's just talk about ETS for a moment. So ETS was based on a principle of decomposition, which has been around for 100 years or so. And so the principle of decomposition is that any time series data that you have, you can effectively separate out into three core components. One describes the overall trend, which is where your time series is heading over a long time. Second is the seasonality, which is the periodic sort of nature of it, often because of the day of the week or the time of the year. tend to sell more barbecues in summer than you do in winter, so you kind of have this sort of very periodic type of nature to it. And then anything that can't be fit into one of those two camps then gets sort of bundled into this sort of third bucket of randomness stuff, which just can't be described with that kind of model unless you try to have a more sophisticated model. And so their argument here is that in order for your time series to be predictable, have good predictable qualities, you really kind of want to make sure that random component of it is as small as possible, has as small as possible sort of contribution as possible, so that you can use the more predictable components of the trend and the seasonality. So a more general assumption is that the time series can be decomposed in a periodic sequence and a sequence with a smooth trend. Okay, so that just confirms what we were just discussing. Now then, theorems. Oh, crikey. Okay, theorems. For non-periodic patterns, as long as they are smooth, which is often the case in practice. Really? The error is still bounded by an adequate look-back window size. Okay, well, that kind of makes sense. So you need enough historical information to be able to pick out what the trend is, to kind of know, what the general trend is, to make a good forecast, which kind of makes sense. Differences from conventional deep learning models. Following the discussions in Zheng et al. And Ni et al., our analysis of linear models offers deeper insights into why previous deep learning models tend to overfit the data. Linear models possess a more unique characteristic wherein the weights of the mappings are fixed for each time set in the input sequence. This time-dependent characteristic is a crucial component of our previous findings and stands in contrast to the recurrent or attention-based architectures where the weights over the input sequence are outputs of a data-dependent function, such as the gates of an LSTM or attention layers in transformers. Okay. So they're saying, right, because we're using a recurrent type system or an attention-based system, then they're kind of flexible enough to be able to, work with the actual characteristics of the data, as opposed to just having weights that are fixed to individual time steps in order to make your forecast. The time-dependent linear model, despite its simplicity, proves to be highly effective in modeling temporal patterns. Okay. Conversely, even though recurrent or attention architectures have high representational capacity, achieving time-step independence is challenging for them. Okay, they usually overfit on the data instead of solely considering their positions. This unique property of linear models may help explain the results of the linear models where no other method was shown to match the performance of the linear models. Okay, so basically they're saying, if your scenario is one that can be simplified, and they argue that in practice most time series models, most time series data can be simplified into a periodic pattern and some sort of trend, that once you've decomposed your time series into those two components, then you can describe them using simple linear functions and then combine them as you would do with a Holt-Winters model to produce an accurate forecast. And conversely, using a transformer-based architecture or one that has more capacity tends to overfit because it kind of looks at specific training examples and looks at particular training examples instead of learning the underlying sort of seasonality and long-term trend characteristics. Okay, so we finally get onto the architecture itself. Let's just read this first paragraph. So, expanding upon our finding that linear models can serve as strong candidates for capturing time dependencies, we initially propose a natural enhancement by stacking linear models with non-linearities to perform multi-layer perceptrons. So classic sort of MLPs. Common deep learning techniques such as normalization and residual connections are applied to facilitate efficient learning. Okay, so we're kind of in this realm of just using a linear feed-forward block with a linear transformation, an activation function rate you typically drop out, and then in addition to that they're also using normalization, so batch normalization or instance normalization, something like that, and then residual connections, all popularized by work 10 years or so ago in the computer vision type world. To better leverage covariate information, we propose the application of MLPs in the time domain and the feature domain in an alternating manner. The time domain MLPs are shared across all of the features, and the feature domain MLPs are shared across all of the time steps. Okay, so this kind of plays back to our lovely diagram back up here, where we're talking about flipping the dimensions. And then, so you flip the dimensions and then pass it through an MLP block. And an MLP block will then learn either the time temporal patterns, or it would learn the channel patterns, and then by layering these on top of each other, you kind of hope that it's going to do a good enough job of representing both time and channel mixing all together. The temporal projection is identical to linear models. Okay, so map the time series from the original input length to the forecast length. So basically all they're saying here is they need to apply some sort of linear projection to cope with the fact that your context window size could be of a different size to what your forecast horizon is that you want to forecast. So if your look back window is, I don't know, like if your look back window is 96 time steps and you want to forecast 36 time steps, then you'll need to do some sort of projection to transpose that historical context into the same to the required number of time steps for your forecast horizon. But obviously if you have context length that's the same as your forecast horizon, then I guess that kind of wouldn't be necessary. Residual connections and normalization. All right. They kind of talk about this 2D normalization, but effectively it's just a 1D normalization. They just bundle all of the data into one dimension and then just apply a 1D normalization to it. Their experiments, they do it on the M5 data set. This is their adaptation of TSMixer to handle auxiliary information. So this historical data, the historical time steps, that's kind of, what we have to do. So that is TSMixer in its own right. And then they might have future covariates, time-dependent covariates. That's the sort of promotions type of scenario. And then they have static covariates. So that's what do they have in here? But that's like the location stuff, so your electricity location. And then they kind of merge that all together and then do their mixing stuff. So they kind of extended TSMixer to be able to handle all sort of information. Then they start going to their results and talk about the efficiency bit. And so these are sort of these data sets are classic multivariate data sets that have been used across all of the sort of autoformer, informer type of systems. ETTH1, ETTH2 are ones that I've used in the past. M5 is one that kind of sticks out because that's kind of not been, you don't often see that as a benchmark. And so they have their results here. So TSMixer on ETTH1, and we'll look at this a bit more closely. Yeah, I'm pretty sure that's the forecast horizon. So ETTH1 336 forecast horizon 0.420, 0.431, whatever that's worth, we'll find out. According to them, it's better than temporal fusion transformers and all of these other ones. Okay. And then ETTH2, H just means that they're hourly readings. Okay, so hourly readings, I think, from some transformer thing, and you're trying to predict what the temperature is of a transformer. Okay, on an hourly basis. So 336 time steps into the future on this one. 3.361. And the other thing is these are all normalized results, so everything, all the data gets normalized, which I'm not a big fan of, but never mind. So anyway, the point there was our model's good, other model's bad. The effects of look-back window length. So I think this is kind of an interesting study to see how the change of look-back window or context length impacts performance of forecasting accuracy. And you would sort of instinctively think that if you have a longer context length, you're providing more historical information, then you would get a better result, a more accurate result. And indeed, I think that is the conclusion that they come to here. Although it does, as they sort of point out, it starts to plateau. There comes the point where your context window becomes so large that you sort of, it's kind of like diminishing returns. You stop getting good performance improvements. It kind of flat lines out. Transformer-based models, what do they say here? Transformer-based models such as transformer, informer, autoformer, photoformer do not benefit from look-back window sizes greater than 192 and are prone to overfitting when the window size is increased. Yeah, I mean, that's true, but I guess, the other thing to think about there is if you increase your window size, then you effectively decrease the number of training samples that are available to you. Because you have less windows to choose from because each window from your training set is so much larger. So it may just be that it overfits because you don't have as much training material open to you. In comparison, TSMixer demonstrates a superior ability to leverage longer sequences and better generalization capabilities than other multivariate models. Okay. So let's check this out then. So figure 5, performance comparison and varying lookback window size L of linear models and TSMixer. Okay, so we're not actually, so we're comparing this to the linear models, not to transformer models. That's a shame. So for forecast horizon of 96 time steps on this weather data set, they're saying that if they provide a context window of 96 time steps, then their MSE mean squared error is higher. And then if they reduce that down, if they increase the number of time steps they provide in their context to 336, then it comes down a lot. But then you don't see sort of any sort of significant improvement after that. Similar sort of pattern with the linear models. I mean, yeah, it's a similar sort of, basically it's the same pattern, right? For linear models and with TSMixer. Just we're starting off from different levels of accuracy. Okay, makes sense. Okay, so let's just come to their conclusion. So we propose TSMixer, a novel architecture for time series forecasting designed for using MLPs instead of RNNs or attention to obtain superior generalization with a simple architecture. Our results at a wide range of real-world time series forecasting tasks demonstrate that TSMixer is highly effective in both long-term forecasting benchmarks for multivariate time series and real-world large-scale retail demand forecasting tasks. That's the M5 dataset. Notably, TSMixer is the only multivariate model that is able to achieve similar performance to univariate models in long-term time series forecasting benchmarks. The TSMixer architecture has significant potential for further improvement, and we believe it will be useful in a wide range of time series forecasting tasks. Some of the potential future works include further exploring the interpretability of TSMixer, as well as its scalability to even larger datasets. We hope this work will pave the way for more innovative architectures for time series forecasting. Okay, right, let us take a look at their model flow. So here I have a local implementation of TSMixer, right? So this whole module contains everything that you need to run TSMixer. It's about 600 lines long, and I am running through the debugger, and so we can go step by step to look at what the code is actually doing, and we're going to look at this from a univariate perspective, because I think that will simplify things a little bit. We'll just step through the code. So the dataset that we're using for this is one of the Monash datasets. I think it might be car parts. It doesn't really matter what it is, at least not for the purposes of understanding what the model architecture is. So I've just kind of forwarded on to the forward pass. So this is our sort of entry point into doing inference or training. So we have an input tensor, and let's just go to the debug console. So x hist shape. Okay, so remember before I was talking about the size of the shape of the input tensor. So this is the same sort of thing. So we have 32. So this is the batch size. So 32 training examples. 15 is the time context. So we're going back looking at 15 historical examples. So 15 time steps back. Univariate, so we're looking at one channel. Okay. Now the first thing we do is we have this self-revin. Now what's revin? Revin stands for reversible instance normalization, which is a very fancy way of saying that what we're interested in is effectively using like a sklearn standard scalar type mechanism to normalize the data. So all we're doing here is transforming our input. Let's just go through it. Transforming our input to subtract the mean and divide by standard deviation. So Revin also provides the ability to attach onto it a sort of a linear layer as well. And so the idea here is that we do this transformation from our raw data. Let's see if we can see our data. Let's just pick the first one. Oh, I chose car parts, so it's just I should have chosen a better example, but never mind. So this is intermittent demand type scenario, but you can see anyway there are two things that were sold on this day, and there was one thing that was sold on this day, and then there are no things that were sold on these days. And so what we're looking for is to normalize this. So let's just step through this process. So here we are getting the mean, for getting the standard deviation. Now that forms the statistics that it's describing. And then we're going to do the normalization. So subtract the mean, divide by the standard deviation, and then if you optionally set for your an additional linear layer, then it will apply that as well. So let's just check out what our tensor looks like now. So here we go, lots of numbers. Now this should now have a mean of 0 and a standard deviation of 1. So that's that. Then we can come out. So now we've normalized our data. Let's just mark down on here what it is that we're finding. So if we get skill issues, help. Oh, here we go. Right, a post-it note, that'll do. Right, Revin. Should we call it Revin or should we call it normalization? Revin normalization. Transform. And now let's just assume, because we're not complete numpties, that we're going to have to do an inverse transform before we return our result. So there we go, that's part 1 done. Now then, what comes after normalization? Well, we have these mixer layers. So what are mixer layers? So let's dive into that. So we have this mixer layer block. Okay, let's just see what we're doing here. Okay, so we build our mixer from number of blocks that we built. Number of channels, so number of blocks. Where's the number of blocks? Okay. So it's not particularly intuitive, but I think what we're trying to get to is we're building a stacked layer of these blocks, which will run in sequence. And okay, so we're using effectively three blocks that are stacked on top of one another. And then each block has this time mixing component and our feature mixing component. So let's just mark that on our lovely board. I'm sorry, we've got three blocks doing this. So let's come back. Let's step into here. So we're in our time mixing module. So X temp. Right, let's just remind ourselves of what our input tensor is. Okay, so we're still in our original shape. So 32 training examples in B, 15 time steps historically, and then one channel. So the first thing we do is we call this function feature to time. So let's check that out. Okay, so we're just permuting the time and channel dimensions. So we're swapping them around. So now if we do our X shape, we should see our original tensor was 32, 15, 1, but now we've permuted it, so it's now 32, 1, which is now the channel dimension, and 15 is the time dimension. Okay, so we're done our swappity thing, and then we are calling this function here. So looks like FC fully connected. So linear layer activation, and I know what that is, but let's just prove it to ourselves that that's what it is. So this is a ReLU. So we can go over that, and then we can apply dropout. Very classic type of thing to do. And then we do time to feature, and there we go. We can guess what that does. This just swaps the dimensions back around. So now our variable we've assigned this to is xres. So we're expecting xres to be back into the same dimensions as our original input. We haven't actually signed it yet. Donut. There we go. Okay, so xres 32.15.1, and just to make sure that we still have x as the same. So here we are. So xres is our residual changes that we've just created by going through these transformation steps, and then x is our original tensor that we put into this function. And then what we're doing here is we are adding together our original tensor and the xres. So this is kind of, classic type of residual network thing, where effectively what you'll want the network to do is to learn the delta of the transformation that you want to do rather than replace your input. So you just want to augment your input with whatever changes are necessary to get it to whatever you want it to be. So we're adding those two together here, and then we're calling this thing self-norm. So let's find out what self-norm is. Right, so we have this specific class which inherits from Pytorch's batch norm 1D. So batch normalization. And then here we are effectively merging together our time channel and our time dimension and our channel dimension to be one thing, which for us in a univariate scenario doesn't actually do anything. In a multivariate scenario, if you had two channels and 15 time steps, then what this would do is this would reshape it into a tensor of size 3230, because we'd have to multiply the time and the channel dimensions together, and then 1. Okay, so that'd be 3231 for 2 dimensions. But we're not doing that with this, we're doing univariate. And then we're just calling batch norm. And then here, okay, so, and here we just convert it back to our original shape. Okay, right, fine. Easy peasy. Let's try and put some things down here. In C dimensions. Permute T in C dimensions. Where am I? Oh, here. Linear, redo, linear. Relu, drop out, drop out, and then permute back. X equals X plus, stop it, X res, X res. Right, we all know what we're talking about there. So we're just making the, this becomes X res, and we add that onto our original input, and then we do normalization rate. So, hurrah! Okay, that's time mixing done. Let's go on. Feature mixing. Self projection. Okay. So here, you remember we were talking about we'd have to do some sort of projection if the input sequence was not the same as the length as the output sequence. I think this is what this is doing. So let's just see. So if input channels is not the same as output channels, in other words, okay, so actually this is talking about channels, not time steps. Fair enough. So if the number of channels that you're forecasting is not the same, is less than the number of input channels that you have, then you need to do this projection to get it into that space. Otherwise, we're just using identity, right? Not modifying at all. So for us, because our input channels and output channels are the same one, we're not doing anything here. So norm before, let's just check out what norm before is before we start going into it. Norm before, norm type. What's norm type? That's our normalization function. If normalized before. Do we normalize before? Looks like we're going to normalize before. I tell you what, let's just find out what it is. So I don't know. F self norm before. Right, okay, we're doing normalization before. Right, okay. So this is going to get called. Yeah. We do our reshape thing that we don't need to worry about. Okay, so back to here. It's interesting because we've just done normalization. Then linear layer activation function, which we have already established is ReLU dropout, and then another. Oh, hang on. Let's start bringing this down. So linear ReLU dropout. Let's get those boys in. There we go. Then we have another linear layer, FC2. Where's that? Okay. So we just got some effectively hidden dimension. We're going from one dimension to 256. So we must be going from one dimension to 256 dimensions. Been going through activation and dropout, and then we have the second linear layer where we go from 256 dimensions back down to 1. Then applying dropout. Then, let's go forward a bit. Then we have our projection. We're adding on our projection. Okay. Because this linear layer has already projected it into the output channel space. So then, okay. So this, right. So this allows us to do the residual residual connection basically. So we don't want to change the input really, but if your input channels is different from your output channels, then you have to. And so what this does is it just projects your input into the same space as your output channels, and then you kind of pretend that this is basically the equivalent of your original input. And so you then have your original input projected, and then you add on the residual, which I suppose this should really be, the X here is the residual, and then you have your return value, and then I assume that we're not doing norm after. Let's just go forwards. Yeah, no, I don't think we are. So, and then there's a special case of this where you need to do that projection if the number of channels is different. Okay. And then I think it's just repeat 3 times or another 2 times. Let's just go step over these ones. That's the second time, and then this is the third time. And then we should be done, right? Yeah. Okay, so that's our 3 mixer layers done. We have this featured time. So this was the permuting the dimensions around. So let's just remind ourselves where we are. I think we're back in our original dimensions. So x dot shape is, yes, so 3215.1. And then we're assigning x temp to be the mixed switched dimensions. So let's just forward on. We don't want to see what feature time does. We know what that does. So now we have x temp, which let's just verify that it is. Yeah, so 13, 1, 15. So the time dimension is now the last dimension. So temporal projection. Okay, so temporal projection, this must be doing what I was thinking about, where if you have different context lengths from forecast horizons. I hope it is anyway, otherwise I'm going to look like a muppet in a minute. Where is it? Where have you gone? Temporal. Yeah. Right, here we go. So projection from our input look back window, sequence length, context length, however you want to call it, to prediction length, forecast horizon, forecast length, however you want to describe that. Perfect. And then we assign X to be whatever that projection is, having then permuted it back. Let's just go over that. Okay. So let's just kind of write this down. Let's go with green. Send him back. And we'll put him in here. And then, come here. That's better. Then we do a linear layer. So context length to forecast horizon. There we go. Right. Now, are we done? I think we might be. Let's just step over that. Here's a denormalization, which we already have captured on with our lovely post-it note. Then step over, step over, step over. Done. We're out of it. So we're just putting in our formatting our output basically. So we've got a forecast which is for 12 time steps. So there we go. Perfect. I mean that's pretty straightforward, I think. And that's basically all there is to it. I mean, obviously it's a little bit more complicated if you have the additional channels involved for multivariate, but you know, normalization, and then they have these two blocks which are just very conventional MLP blocks, linear, ReLU, dropout, residual connection, normalization, and then do that with the time dimension is the last dimension, and with the feature dimension is the last dimension. And then you need to do this sort of little projection trick at the end just to make sure that you're projecting into the forecast horizon that you want to. But yeah, I mean, that's kind of it. So I think it's nice. Let me just show you one other last thing before we wrap up. We want Google Chrome. Yes, we want Google Chrome. Okay. So, as I said earlier, I have been doing some benchmarking for the forecasting data org project and have just gone through and done TSMixer. And these are, so across the columns are various models that we've benchmarked before. And each row is a separate data set. So there's about 40 data sets in total. Things in bold are the best. And what you can see is that Yeah. So things in bold are the best. And TSMixer actually, I think, performs pretty well. I mean, look at this. So the best one here is this Gluon TS V4 neural network points. This is maze, by the way. These are mean absolute symmetric errors. So the lower the number, the better, basically. Sorry. Yes. Been doing this too long. The lower number, the better. So 0.769 and TSMixer did 0.792. So that's pretty close. And then Kaggle Weekly 0.595 versus 0.582 on in hits. And let's pick another one. Pick another one further down. Traffic Weekly 0.099 versus 1.04 from Times FM, and that's questionable because I think there's probably some data leakage with that. But overall, I would say that this TSMixer has performed pretty well across the board. There isn't any sort of individual result on here that makes you think, I wouldn't go for that in that type of scenario. So I think it performs well, and would definitely be one that I'd take a closer look at, considering that it can, because it does have a few number of parameters, it does train pretty quick, so you can really kind of get this set up pretty fast and get some good benchmarking results out of it. And bear in mind as well that when we're benchmarking these things, we're using a fixed set of hyperparameters, so you could tune this pretty easily, I would think. And again, because training is so fast, that whole sort of process of doing tuning is going to be pretty time efficient. So yeah, overall I would say go check out TSMixer. It's a nice model, simple to understand, simple to use, does a good job. If you've made it this far, well done. I'm proud of you, and I will maybe do another one of these in the future. So I'll see you later. Thanks. Bye.